Mr. Shen. Welcome back to your best nightmare. So, apparently, I am having problems with my grades again. Therefore, why this video exists. You must be wondering why there isn't a green screen or I'm not wearing a fancy suit. To be honest, we ran out of budget. Apparently, there's this thing called time constraints, in which I have to rush out of mastery within a due time. For example, a test that was just occurring last week. Thank you. So, this time, in response, I've got these. So this time, I'm going to show you what we can do with a limited budget and try to bust through the applications of derivative. So what is the applications of derivative? In essence, because I already got a good enough grade at the first two topics, i.e. derivative and limits, I'm not going to go over them. Unlike my usual self, this time we have time constraints. So, we're going to talk through how do we use derivatives, double derivative, all of that stuff. No straight line motion. So if you're just going to use this as review material, go to College Board and Khan Academy, because College Board objectively is bad company. Now, the first topic on our list is also the easiest. It's called the derivative of inverse functions. In essence, if you remember a long time ago, an inverse function is a function in which y equals to x, or you swap x and y. So, in a derivative world, we've got these two equations. I can show you the proof later, but the essential gist is this. In order to find the derivative of an inverse function, we can use the original function in order to find its inverse. For example, so we've got two examples here. Here's a harder one, here's a very demonstrative one. So as per these two equations that basically tell me that how to find the derivative of an inverse function. In essence, the reason why I want to use this kind of thing is because either the inverse function is too hard to find, or because you just want to be slightly lazier, but actually if you just inverse the function itself and then find the derivative, it's sometimes faster, so I don't know why you would use this. I did this specifically because the AP test asked me to. So these are the two equations. So as you can see, according to this equation, we're trying to find the derivative of the inverse function of f. So f of x is 2x. But we don't need to find the inverse function because, according to its derivative, it's just a single line. It's going to be 2 every single time. So in a linear setting, all you have to do is just throw it under the bus, or the denominator, and you'll get this. The answer. Now, let's take a look at a slightly harder example. Let me just walk over here. This is an example in which the problem is not linear. So, in that condition, you'll have to do a little bit of more work. But it's not much. In fact, if you just derivative this, if you're skilled enough, this is probably going to be easier. So first thing, as per usual, you need to first find the derivative of f of x, which is, in this case, is 4 of x. And the inverse function of it, swap x and y together. Rather, you'll find the inverse function of x is this. Square root of x divided by 2. So this, in essence, means that we can... Oh wait, I forgot to write the solution. Okay, I can do it now. So we're trying to find the derivative of this, which is this. So we're trying to first throw it under the bus, aka throw it into the thing, and we need to throw the function of the inverse equation in here, and we have this. So wait, this is square root of that, okay? So that, in essence, means that, yeah, this is the derivative of that entire section. This this is, wait a second, have I done it in inverse? Oh yeah, I did it in inverse. So that means that we're trying to find, what are we trying to find again? Oh yeah, we're trying to find, yeah, that's it. So this is, theoretically, what you will get if you use this method. I didn't really think about this problem a lot, because it's super easy. On we go to the next topic. So, next up, the topic we have is find the increasing and decreasing interval of any given equation. This thing will be applied to every single calculus equation that you will ever encounter, and it will haunt your dreams for the entirety of your life. But actually, this isn't actually quite a bad thing. All you have to do is to determine the moon of dy dx. So, as you all possibly know, dy dx, the derivative of the equation, is the rate of change, aka the slope. So it's going to measure whether it's increasing or decreasing at a given interval. So we can find if the slope is positive or not, meaning whether it is going to make the function go up or down. So in this example, very rudimentary example, we have two sides of the equation, here being the middle where dy of dx equals to 0, just okay. Okay, so as you can see, the slope is increasing here, while after this point, the slope begins to decrease. So theoretically, all we have to do to see if a function is increasing or decreasing is to map out when does it change positivity, and when does it change positivity, and when does it go from positive to negative, which is also known as critical points. Next thing I'm obligated to explain is the concept of critical points. That's when the derivative is 0 or undefined. Essentially, whenever dy dx equals to 0, or whenever it means something. For example, in this extremely crude equation that I just made up on the spot, the critical point is going to be 1, -2, or -3. But being a critical point doesn't necessarily mean it's going to affect the concavity, how it's going to increase or decrease the entire equation. As I have told you before, these things only matter when they're changing from a positive to a negative, or negative to a positive. These are the things that are important. And if they are not those, it's practically useless. But they are still important, even though they are not quite important. One of the other things is that we express the changingness of dy dx through a number line. You have seen this trick before. It's in my other videos. You basically just map out when it's going to change negativity, when it's going to change. The interesting point is that if there is a discontinuity, like in this case, it's probably going to cut the section in half. For example, let's just say this is a completely non-related example here. We've got a section of increasing here, a section of decreasing here, and a section of decreasing here. And let's just say it's -1 to 1. So, if there is a discontinuity anywhere between this, we'll have to express this area of increasing as -1 to, I don't know, 0, -1 to 0, and 0 to 1. This thing, just a reminder, doesn't include the values themselves, because these values at the point is 0, and they're not positive or negative. We are not done yet! Next up, we have the concept of local maxima. Basically, the local kings or lords of that specific region. So, in every single case, when the increasing and decreasing interval changes positivity or negativity, it's going to create a local maxima, aka a regional king. For example, in this particular region here, let me just quickly swatch pen, it is increasing, right? But slowly and slowly it's going to hit a peak and it's going to begin to decrease. At that point, we call it a local maxima or a local max. A local maximum. This basically means that this is one of the hills of that particular region. And when the opposite happens, when it goes from decreasing to increasing, it's going to turn into a local minimum, aka the lowest of that hill. As you can see in this graph, there can be as many local maxima as you wish. There can be, I don't know, a dozen in a given graph. There can be a couple thousand. I don't know. Normally you only encounter 3 or 4. That's what I normally encounter. But you have no idea what your teacher will throw at you, so be vigilant. There's also the idea of absolute maximum or absolute minimum, which is like the highest section of a graph given the interval. Because normally graphs are infinite, so we can't really determine if they are going to be positive. So sometimes there can be infinitely large or infinitely minimal depending on things, but we normally are given an interval. For example, in this interval, let's just say from here to here, we can see that the highest point clearly, aka its absolute maximum, is this. So this will be its absolute maximum for this entire interval, while this will be its absolute minimum during its interval. And we're done with this section, I think. Next up, we have the concept of concavity. Concavity is essentially when you see a function and see, oh look, it's pointing down. Oh look, it's pointing up. Oh look, it's pointing down, it's pointing up, and so on and so forth. So, whenever a curve is like facing downwards, for example like this one, we call it concave down because it's bending backwards. And then this is called concave up, or this, which is a more clear example, we call it bending upwards. Now, how do we know if a function is concave up or concave down? To do that, we need second derivative, also known as d squared y over d of x squared. Basically, do the entire thing that I just talked about and apply it to f of x f prime of x this time. So, to find second derivative, all you have to do is to throw derive the derivative again. It's that simple. Although you might need some chain rules at times, it's going to be quite normal at times. You'll get used to it. You'll need this in order to survive on AP calculus and things. So we're trying to find something similar to critical points, although it's not called critical points anymore. It's called points. O inflection, or of inflection if you're not as lazy as I am. This, in essence, is when the second derivative changes from positive to negative, or negative to positive. You get the gist. So, in order to find... So, basically, whenever this changes from concave up, down to concave up, for example, in this green line, where at this theoretical point it's going to change concavity, you can see that that is going to be a point of inflection, and that is going to also be a point of inflection. Whenever it changes concavity, it's a point of inflection. Just throw everything that I just told you about it, and throw it into d second y, throw in the second derivative instead. But because of this, and all of these new knowledge that we have, there's a terrifying truth. Now let's say the burden of knowledge might be a little bit much. As you can see here now, we have no way to hide from the weird equations, aka the ones that have barriers in place, also known as discontinuities in place, and the kinds where we used to just lollygag around, playing in the fields, guessing where those points go. Now, because we can get derivative and whether they're increasing, decreasing, and how they're going definitively, we now have to sketch them accurately. You're gonna see me burning up there, right at the top of where this entire thing is. I'm dying because of this. Now your teacher isn't going to throw this around you because it's going to be a hassle for them to grade too. And also because it's very hard to really grade you on this because it's very laborious. And this is probably only going to happen inside the actual College Board test. But in order to find the graph that you want, you need to find the intervals of concave up and concave down, intervals of increasing and decreasing, critical points, inflection points, and also relative maximum and minima. Now, to be honest, you don't need critical points. They're kind of useless in my opinion, but you need the critical points in order to find the relative maximum or minima. So you might as well find them, just in case. There's also other ways that you can help. Y-intercept, X-intercept, those things are going to help quite tremendously. Remember how you used to graph these, apply these knowledge, find the discontinuities, vertical, horizontal, etc., and apply them. This sounds simple, but it isn't. Because all the questions and the equations I've thrown at you at this point is a bridge. Like, they're very simple. So, in essence, fear this part. And thankfully, Mr. Shen doesn't really throw a lot of these questions at us. Now, I really want to demonstrate the madness of this to you guys, but I can't in this given space. So, here's a video of me that's covering me currently. You can see me trying to do the entire thing. I don't know how long it's going to take. It depends on the person. I haven't done this type of question because he doesn't throw these type of questions on exams. Because it's going to take an average about 10 to 15 minutes. Or maybe 5 minutes if you're really, really powerful or number crunching. I'm not the most technical guy. So, here's the video. Are you enjoying it? I hope you are. It's taken me, I don't know, a while to get the recording setup done. I think it might have ended by now. Next up, we've got related rates. Now you must be wondering why the backboard behind me is very empty. And the reason is, it's all word problems! Now the problem with word problem is that I can't really explain how to solve things deeply. Because related rates is a car crash in terms of themes. It can have a variety of different questions. For example, I spilled oil over the Pacific Ocean. That's a possibility. So then essentially, all you have, this type of question expresses a certain value, x, whatever. In this variable, it's going to be an oil spill over the entire thing. We're trying to find the rate of change of the area, and they have given us, for example, the rate of change of the radius and what the radius of the entire oil spill currently is at that given time. Wait. Yeah, this is more accurate now. So, in order to do this, we will have to first find the equation for the area. Not all of them are a circle. Sometimes there are some more devious problems here and there that includes a circle within a circle. But in this case, it's just pi r squared. And we have to derivative it, find a way find a way to put the value of dr dt into the equation because we're trying to essentially find the rate of change of area, which is dA dt. Now the unit that they have given you is going to be very important because that's going to be a trick somehow. I can see it. So remember what unit they have given you. In this particular instance, the t that we're dealing with is seconds. Do derivative. The math is simple. By finding the equation and knowing how to really get the equation is going to be the hard part of going to be many things. And there's also a subversion of this related rate problems. Now, the next thing is theoretically, which is a subsection of related rate, I don't care, is optimization. Optimization basically asks you to find the equation's local maxima or minima. Now, what is the equation? The problem is every equation is different. So, the main part about this isn't actually about derivative or finding the local maxima or minima. That part is simple. The problem is you gotta find the equation to begin with. Now, let's just take a very simple sample of optimization questions. This is me on the way to my friend Davy's house. So in order to get to Davy's, I need to cross over a river, which is about 10 meters long. I can approximately this is a little bit too little. 100 meters, that's a little bit better. So, assuming that I can row at a rate of 10 meters per hour, I can actually row for 10 meters per hour. I can row 10 meters per hour. And then I can walk for 2 meters per hour. All of these numbers are very fake. So, the question is, where should I park the boat so that I can get to Davy's home the fastest? Now, the main difference between related rates and optimization problems is that optimization problems ask you to find the best solution. Or, in other words, it requires you to find an equation that you must derivative it. In this case, I need to find where I need to land the boat, so let's just call this, I don't know, X. Where I need to land the boat. So, the distance, so the time that I need to find the thing, which is what I'm trying to get the fastest time of, I need to first find the time that it would take me to cross to this point. So, to do this type of question, you need to remember a lot of equations. Because I just finished my SAT, I have a moderate knowledge of what I'm going to do. So, let's just say this is 20 meters, and this is the point where let's just say, 20 minus x, and this is x. So, adding these together, you got 20 in total. So, let's just say that 10 squared plus 20 minus x squared. This is going to be a distance from me comfortably on my home boat going to a place that I'm going to park the boat. Now I need to add the extra distance of x. Also, now I need to add the extra distance of x, which is the thing that I'm trying to find. And then let's just apply the rates here times walking speed, and times like my walking speed, which is 2. And this is the kind of things that they want you to do. Now, every single thing is different. This is one of the more prominent questions, and it's very cliche, in terms of as questions goes. But there is a lot of varieties of this type of questions. To name of which, they might ask you how to find the most amount of cells, yada yada. The main difference between optimization and related rates is that in related rates, they'll most likely ask you a question that includes rates. In optimization, that's probably not going to happen. Sometimes it's just going to be like mentioned a very little. But it's not going to be. It's not going to ask you the precise time. In related rates questions, they do. Remember that, and just see which one is which one asks you to find the maximum. That's about it. Now, the next one, if you're not French, you might read it as L'Hopital's rule. And frankly, I really want to say it that. But in order to solve this type of question, as the pictures show, we have to deal with the French. Now, L'Hopital's rule. I don't know if I'm butchering this correctly, but I'm saying that every single time I'm saying that. In essence, here's the proof. So, first we have a normal fraction here that is going to a limit. If you don't know what a limit is, pause this video, go back to the beginning of AP Calculus. It's still not too late. You'll come back later. And we can quickly do some shenanigans here, minusing it by itself, basically using the definition, basically just trying to recreate the definition of limits, which is fine and dandy, I suppose, because these two things are supposed to almost be the same. So, this kind of results in that limits of x to the power of a is the equivalent of f of the entire thing going to a derivative, or the top going to a separate derivative as the bottom. Actually, that's the last case, which is the only case. Now, you might ask, Howard, why do we need to deal with the French in order to solve these type of questions? It's just a fraction. No, because sometimes you're dealing with very bad cases, or as people know, extreme cases. We only use this rule when the limits we have is 0 over 0, or infinity over infinity, or negative infinity over negative infinity. These are the three conditions where we can use L'Hopital's rule. And these are the only three conditions where you get to use this rule, because this thing only works at extreme cases. Now, the problem with L'Hopital's rule, because as the requirement of it, it requires, as you can see, a fraction to work. Without a fraction, this entire thing is a bust. So, what do you do when the thing they want to solve is not a fraction? For example, this. Well, this is a very simple case of L'Hopital's rule. As you can see, this is not a fraction, so we need to make it a fraction. So, you probably know a little bit of a thing called rearranging. So, as you can see, 5x of limit, let's just go with something a little bit easier. So, x is basically the same as this, right? Because, if you can see, it's basically 1 times x of 1 equals to x. You see, this is the same thing. So we can do that to the x here. We can force it, torture it, into a fraction. So we can basically turn it into like this, x to the limit of 0 plus. Now, going with only one side is okay. If you know limits, you know limits. So in essence, we can turn it into this. So in essence, we can turn it into this, which is all fine and dandy. Now the next part is very simple. You apply derivative to both sides. Right? Wait, we need to first check if this is 0 or not. Natural log of 0. Natural log of 0 is 0, so this is 0. 1 over 0, that's infinity. Wait a second, what's natural log of 0? Oh yeah, this is, as you know, natural log is a logarithm. So that means that when it's 0, because when 0 is going to approach infinity, essentially. So this is a condition where L'Hopital's rule can apply. So, to use the L'Hopital's rule, we need to do some shenanigans, apply the derivative to both sides, limit x to a function of 0 plus us da 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 da. Anyways, we can just ignore this because you already get the simple gist. This only works in extreme cases, and sometimes we need to force a certain function into becoming a fraction for this thing to work. There's also another subsection though. Because of the French, we have another shenanigans on our hands. I like to call this thing force E, where we force Euler's number into any given equation. So, at times we encounter equations that we can't really apply L'Hopital's rules on, and they still demand us to use L'Hopital rules. On those occasions, we are forced to resort to extreme means, aka this equation. This equation transforms basically any single thing into E, and then we can get the limits of this instead, because it in essence equals to x. So by that we can first grab the limits of natural log x, and then we can do other things ourselves, turn it into a fraction, yada yada, and then we'll get our answer. This is a very complex thing, so future me might intersect right here and tell you more about this entire concept. So, next up we have the mean value theorem, which is also, in a way, kind of a word problem. That's not really. So, the mean value theorem essentially states if a function f of x is continuous from interval a to b, and it is also differentiable within those intervals, not including a or b itself, then there will be at least one derivative of which value, and it is going to be at least one value c, in which the derivative of this entire thing also means that one of the tangent line is going to equal to the slope of a to b. This seems simple, right? But in order to make sure that this theorem applies, you need two fundamental things. You make sure that it's continuous from a to b, and also differentiable from a to b, which shouldn't be quite a hard problem, but it is. Now let's get into one of my worst nightmares. 2x to the power of 2 over 3 is not differentiable. No! Now the problem with this monster over here that cost me one of my grades is that its function in essence looks wonky. It looks like this. Something like this. So, this at this particular value here is 0. So you're trying to figure out any single point that makes this type of equations 0. Specifically 2 over 3. Because that is a value that will bring you trouble for eons on end. On this specific point, as you can see, it is two slopes converging together. So at this particular point, you'll at once get like a slope like this and a slope like this, which makes this, because derivative is based on limits, this makes this non-differentiable. So, in other words, the second half of this particular thing doesn't apply. Remember this. This is going to haunt you forever. Now, we're back to local linearization. Local linearization is a very what's the word, fancy way to approximate a value. So when working with these kind of stuff, it is often that we get like a value that is very hard to pinpoint or very hard to work with. For example, for the function of y equals the square root of x, a hard value to work with could be, let's say, 4.01. This value is not going to be very popular. Unless you have a calculator, it's going to be very hard to actually get the pinpoint value that we're looking for. So, when that thing happens, we can use something called derivatives and make the problems go away. So, we can approximate the value by creating a tangent line at a value that is easier and more accessible. For example, 4 and 2. So, this will basically create like a small but still semi-accurate approximation of the value which we call L of x. So, the rules are A should be close to x, at least to some proximity, and plug into this equation. Now you might say, Howard, this equation looks very, complex and fancy. It's not. In fact, it's actually a very single thing. If you just squint your eyes a little bit, you'll discover that a function is just a slope point form. It is just literally the slope point form. Look at this. You have the original value, the value that you're approximating. M is dy dx is basically just a slope anyways. As we said, according to the definition, it's a slope at that given point, aka the tangent line. And then we basically pick a point that we're trying to find, basically this. And we're trying to get the output value of y, aka this. We're basically turning it into a linear function. So that's about it. One of the interesting things, however, is that when we're dealing with these kind of things, for example, when we're doing local linearization on a graph that is always concave down, you'll find one very interesting thing. We're constantly overestimating. We're always overestimating the particular function. Look, there's always going to be a minor gap between what we're approximating and what we're actually getting, so we're always over approximating. The inverse of the problem happens when we're dealing with a graph that is concave up. For example, let's just say this. If we draw a line that's here, 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 you'll basically always find there's going to be a gap between the value that we're trying to get and a value that we have approximating. So on this particular occasion, we're always underestimating. And with that, we're finished! Finally! Now, Mr. Shen, I'm not asking for a lot of grades, but please at least salvage my grades just a tiny bit. That would be very helpful. I mean, also, if you can, please look at my notes for related rates. That is also very important to my grades, and also to my values as a student. Not really. It is very important to me, personally. To you, possibly not. Now, here's a little speech in case that I die next time also. Please don't kill us with, whatever that you're going to throw us at. You're just going to send us straight into the burning pit at this rate. A lot of us is failing. Please save us. Make it a little bit more graspable for us poor high school students. We're not really poor, but poor emotionally. Please help us. Please. 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 Please.